So in this lecture, we'll study the viscous potential flow theory, in which the flow is potential and that the viscosity is not zero. Actually, the idea came from the Navier-Stokes equation. As we know, the Navier-Stokes equation is rho dq by dt is equal to minus gradient p plus that external force F plus mu del square q. So previously, when we were using the inviscid potential flow theory, it was assumed that mu is zero, and as mu is zero, this total term will be zero, and so the equation, the Navier-Stokes equation, changes into the Euler equation. And if we know that the Euler equation is easy to solve, and in that case, people have taken q as gradient phi, and sorry, that it is gradient phi, and then we solved it for the incompressible fluid. But in 1994, it was an idea given by Joseph that we cannot take mu as zero. It is not always possible to take mu as zero, because we know that all real fluids have some viscosity. So what we did, basically, we have taken del square q is zero. And why del square q is zero? Because we have taken the flow as potential. Flow as potential means we have taken the flow as irrotational. That we have already discussed. If the fluid particles do not rotate about their axis when they are moving, so in that case, basically, the curl of viscosity velocity will be zero, because the flow is rotational, so vorticity will be zero, as curl of q is zero, and the domain is simply connected with the continuum hypothesis. So q can be written as gradient of phi. In that case, del square phi can be written, del square q, sorry, del square gradient phi, which can be written as del of del square phi, can be written as del of del square phi. And as the fluids are incompressible, so divergence of q is zero, as we know from the equation of continuity. So del square phi is zero, and then this term goes to zero, and the equation again changes to the equation again changes into the basically our Euler equation, and we can easily solve it. But how we can include the viscosity? So we will take the normal stress balance or dynamical condition at the interface. That was the basic idea behind this viscous potential flow theory. So this was the basic idea behind the viscous potential flow theory. We have already studied that the viscous potential flow theory is based on the irrotational motion of the fluids and will contain only the effect of normal stresses. In this case, we'll take that the curl of viscous velocity is zero, because we are taking the irrotational flow, so vorticity will be zero, and then in that case, velocity can be written as a gradient of some potential function. And if we are taking the fluid as incompressible, that the potential function will satisfy the Laplace equation. Okay, Joseph has studied this. Joseph has applied this theory to the various instability problems and concluded that this theory gives better results than the inviscid potential flow theory, because we know that in inviscid potential flow theory we'll take viscosity as zero, and if viscosity is zero, definitely it will be an ideal case. It will not be a real case, so data will not be matched with the experimental analysis. And finite Reynolds number, at finite Reynolds number, VPF theory gives excellent results with the experimental data, because we know that the Reynolds number is the ratio of inertia forces to the viscous forces, and as the viscosity is near zero, very low, then Reynolds number goes to very high. In that case, it will be a limiting case of the ideal fluids. But if viscosity is high, then Reynolds number is low, means we are working with the real fluids, and in that case we can just say that the results will be real, and so they will be matched with the experimental data. We know that Reynolds number can be written as rho Vd upon mu. So if viscosity is high, Reynolds number will be low, and so this will give the better results. Also, the no slip condition is basically not will not work in the viscous potential flow theory, because the idea of the tangential velocity cannot be included in the viscous potential flow theory. Later, some researchers have modified this theory, but when we are studying the viscous potential flow theory, the no slip condition, tangential stresses, and tangential velocity will not be considered. Now, we viscous potential flow theory for incompressible. So when we study the theory for incompressible fluids, we know that we have continuity equation as divergence of q is 0. That is, q is the velocity. So in that case, if we are taking the potential flow, q is gradient of phi, and then del square phi will be 0 from these two equations. So this is the basic thing in terms of incompressible fluids. Remember, this is not exactly same in the compressible fluids, but in case of incompressible fluids, this term will behave just like the inviscid potential flow theory. So we'll take phi as the potential function, and as the flow is irrotational, curl q is 0, so q can be written as gradient of phi, and as divergence q is 0, because the fluids are incompressible, will take as a del square phi is 0, and this is a Laplace equation which can be easily solved using either variable separable method, or we have one more normal mode technique that we have discussed earlier. So with that normal mode technique, we can also find the phi. Now we have some boundary conditions, because it is a second order differential equation, so we have some unknown coefficients are there. In that case, the Laplace equation can be solved for the Dirichlet boundary condition, in which the values of phi are given at the boundaries, or for the Newman boundaries conditions, for in which the normal derivative of phi can be given at the basically boundaries, or even the combinations of Dirichlet and our Newman boundary conditions. For example, we'll take just a plane layer, and if we take a plane layer and these two boundaries are rigid, and this is the flow which can be taken as irrotational, and then q can be written as gradient of phi. So if we are taking this one as xy axis, this is x, this is y, so definitely at this point del phi by del y is 0, and del phi by del y is 0 also. And so these are the basically Newman conditions, that at these boundaries the normal derivative will be 0. Or if we are taking that at some point it is given that the velocity is given as ux or some u2, so in that case phi can be written as u2x. So this is will be the Dirichlet boundary condition, and these are the Newman boundary conditions. So by taking the help of normal mode technique, we calculate phi in terms of some unknown constants, and then we'll calculate the value of those unknown constants with those boundary conditions. After that, uh, we will consider the basically condition at the interface of two fluids, because we are studying here the viscous potential flow theory to, and this has to be applied to calculate the instability of an interface. In that case, when we'll take the interface, we have to know whether the um, tangential stresses and tangential velocities at the interface is given, the normal velocities and and normal stresses at the interface is given or not. We'll calculate those basically values, and we have to include them into the analysis. Otherwise, it will be an inviscid potential flow analysis, and that will not work because that has already been done. So in that case, if the tangential component of velocity, if the boundary S is of volume V is given, then definitely in that case the tangential velocity is given like this: us is es dot u, and u can be written as gradient of phi, so we can calculate the component of gradient phi. And similarly, for the normal derivative, for the normal velocity, we will calculate the normal component of u, or we can say the gradient of phi, the normal component of gradient of phi. Here we should remember that these are the directional derivatives of phi, nothing else. Now we'll go for the conditions deriving conditions at the interface. Basically, in inviscid potential flow analysis, it was assumed that the difference in the pressure will be governed by the surface tension at that interface. Means if we are taking two fluids, then it is P2 minus P1 is sigma gradient n cap. N cap is the normal unit vector at the interface. In that case, as we are taking the inviscid potential flow theory IVF, so viscosity is always zero. Now we are basically studying about the viscous potential flow theory. So in that case, in viscous potential flow theory, we must know that how to include the viscosity in the analysis. So to include the viscosity in the analysis, we will use the Navier-Stokes equation, because this condition has been derived from the Euler equation. The Euler equation is the momentum equation for the inviscid fluids, and Navier-Stokes equation is the equation for the viscous fluids. So this is the equation. Navier-Stokes equation is given here. Phi can be written as rho gy p plus rho gy. Remember, we are taking the equation in the planar geometry. So in that case, the stress is given by this tau ij plus tau ij, and this d is because we know tau ij is basically mu del ui upon del xj plus del uj upon del xi. So this is the stresses, viscous stresses, and this d is the symmetric part of strain rate tensor, and these are the strain rates. So d can be written as a symmetric part. It will be the symmetric part because this is the written in the tensor system. So if we'll take the divergence of tau, then it can be written as mu del square u. Here d is symmetric part. As we are writing, we know in planar geometry there will be three components, u1, u2, u3. So here we have taken this component as the vector component, and then divergence will get is mu del square u. Clear? Then we will take the free surface. Remember, we are taking the interface. So in that case, when we are taking two fluids, for example, and this is the interface initially, this one is one fluid, this one is the second fluid. So this is y equal to 0 interface. Now when we perturb it, it becomes like this. So this will be, this height will be eta. So in that case, the interface becomes in perturbed state, basic state, y equal to 0, and perturbed state y equal to eta. As we are studying the stability, that means we must calculate the value when the interface is at y equal to eta. So this interface is taken as y equal to eta. Remember, when we apply the in that our normal mode technique, we will take this one as depending on t and x. So it will be a e to power ikx minus or ikx plus omega t, and that omega will be our concern, because we know that omega will, that real part of omega will basically induce instability if it is positive, otherwise it will be stable. So we will take care of that omega in the problems. We'll later study it. Now, since we are deriving the equation, so the mechanical energy equation for incompressible Newtonian fluid is given by this one. Remember, this is the same equation which can be obtained by multiplying Navier-Stokes equation. That Navier-Stokes equation can be multiplied by the velocity u and integrating in the volume v. That volume, volume v basically bounds the fluid. And A is the surface of the body, and A is a surface which bounds that volume V. So here we have used the Gauss theorem, and using Gauss divergence theorem we can get this equation. This is a very well known equation, and that can be obtained from the Navier-Stokes equation. If you obtained this from the that other equation, you will not get the viscous dissipation term. Here, this equation says the rate of change of kinetic energy of a fluid in volume V is equal to the surfaces, is equal to the external force work on the surface of volume V, the surface tension force work on the surface of volume B minus that rate of viscous dissipation. This D, remember, this is this symmetric part of strain rate tensor. So with the help of this equation, what we can do, we'll calculate the value of this rate of viscous dissipation. See, this du can be written as, here u is, we know that del ui upon del xj, which can be written as del by del xj, and this is del phi upon del xi. So that will be del 2 phi upon del xj del xi. So this du, this colon is nothing but just multiplication. I have not written here d square because we are working with the tensor system. So dxij, and then we use the Gauss divergence theorem. Once Gauss divergence theorem is used, we can take this one as del 2 phi by del xj, and then del phi I by del xi will be the your basically divergence of phi. Using Gauss divergence theorem we can get this term. Now again in vector form, this quantity 2 mu, and we are integrating over the surface AF of volume V is n cap, that nj, then d phi because this one d gradient phi du, and u because that ui can also be del phi by del I. So this can be written as dn. Now this nu, basically we will get the total velocity. This u is the total velocity, so which can be written in two terms, the tangential velocity and in the normal velocity. So this u can be written as the component of normal velocity to n cap and component of tangential velocity. Now when we multiply with this n with d will give you that the normal component of the that strain rate tensor, that normal component n dot d. So we'll get 2 mu del square phi, and this un, basically un dot n, basically the normal component of velocity, and then us with d will give you the component of tangential stresses. This is called the irrotational shearing stresses. So we have calculated this term. This is basically viscous dissipation term. Now the second term, because we know that the term dq by du by dt in the Navier-Stokes equation can be written as del u by del t plus u dot grad u. This second term we have calculated like this one, that this term can be written as gradient of u square. U can be written as u dot u, and one thing you should remember, that divergence u is 0 as we are considering the incompressible fluid. So if divergence u 0, one term goes to 0. You just expand this term, you will get the exact value of this thing. Now, the inertia term, the first term, the rate of change of kinetic energy, which we are saying is like this one. We have just used the Leibniz rule, the differentiation under integral sign. So this rho by 2 is constant as we are taking the incompressible fluid, so that rho by 2 and u dot del u mod u square can be written as mod of u square can be written as u dot u. So u del u by del t plus u dot grad del u by del square. Actually, it is dq by dt square. So we'll use this one as the material derivative, and now use the value of phi in terms of, sorry, use the value of u in terms of the potential function. Del phi by del xi is u can be written as del phi by del xi. Here we have just written it is basically del by del t of del phi by del xi, which can be written as del phi by del xi del phi by del t, and this term we have already stated. So now we put the value of u again in terms of basically phi. We will get this term because here we can just use the cos divergence theorem, and that can be easily seen from these two terms. Clear? We have just taken un, the normal component, as n cap will be there. So u or del phi gradient phi dot n cap will be your the normal component of velocity. So we will get this expression from the inertia term. As we have studied earlier that this equation we are using to calculate the interfacial condition in the viscous potential flow theory. So with these equations, with these expressions, we can get the mechanical energy balance equation like this, where this is the inertia term, this is the viscous dissipation term that was negative in the right hand side. Now it will be positive in the left hand side over the volume, over the surface area dA. This is surface bounded by the that bounds the volume V, and now this is equal to the tangential stresses. As we have already stated that the tangential stresses are zero in the viscous potential flow theory. Remember, it is assumption, it is not say exactly true. Actually stresses are there, but it is our assumption that these stresses should be zero. So if we, as we are taking these stresses are zero, so we will get this equation as 0 equal to 0, and as it is true for every arbitrary surface area of volume V, then that integrand should be 0, and so we will get the equation P rho del phi by del t plus gradient of mod of gradient of phi square by 2 plus zeta plus 2 mu del 2 phi upon del n square is equal to this one. Remember, this equation, this term is basically given by the Bernoulli equation. So this can be written as minus p, and this plus 2 mu del 2 phi upon del n square is equal to minus sigma gradient n cap, and that can be written as p minus 2 mu del 2 phi by del n square is equal to sigma divergence of n. So what we are doing basically, we are taking the basically normal stresses at the interface. In the inviscid potential flow theory, we were taking only pressure because viscosity is zero. Here we are taking the basically your normal stresses at the interface, and so the viscosity comes into the picture, and that's why VPF theory is more important, or we can say very important, in the basically analysis of the stability theory or in the interfacial instabilities. Now that was the basic thing in terms of incompressible fluids. Here we will take as the compressible fluids. In case of incompressible fluid, we have derived the condition Now, because in the incompressible fluid, the equation of continuity was divergence of Q equal to 0. But that is not true in the compressible fluids. In case of compressible fluids, we must know the equation of continuity is not exactly same. It is del rho by del T plus divergence rho into U plus rho into divergence of U is equal to 0, as we are using the VPF theory. So you know that in VPF theory that U will be a gradient of potential function. Remember, in compressible fluid we cannot say that del square phi is 0. No, that is wrong, because fluids are compressible. So in that case we will take the equations as that del rho by del T, because we have taken U as gradient phi. So del rho by del T divergence Q, gradient of rho into gradient of phi, and then rho del square phi. Now these are the viscous stresses in compressible fluid. Remember, del square phi is 0 in incompressible fluid, so stresses are only 2 mu del square phi del I del xj. But as in compressible fluid, this is non-zero. So these are the basically uh, stresses, viscous stresses. Remember, this term minus 2 mu by 3 comes only in the normal stresses when I is equal to j. Otherwise, in the shearing stresses, this is the only term. Okay, this is the Bernoulli equation in case of compressible fluids. Remember, when we say that, can we write the Bernoulli equation in terms of potential function? So it is, the answer will be yes if we are taking the unsteady flow. If the flow is not unsteady, then we cannot take this term del phi by del t. So remember, we are considering here the temporal instability, and in term, and when we are basically saying the temporal instability, that means we have to take the flow as unsteady. Now the last equation is basically pressure and density relation with the adiabatic constant omega, that should be true in terms of compressible fluids. Okay, and so dp by d rho we can just write rho p by this one, and that can be written as c square, where c is the velocity of sound in the fluid. I think the basic equations should be clear. Now uh, this is the kinematic condition at the interface. If two fluids at the interface, they are basically making an interface at the in at some point, then this condition, actually this condition says, if a fluid particle will be at the interface initially, it will remain at the interface throughout the analysis. That means the normal velocity of the fluid will be 0, and this condition can be obtained from there. For example, if we'll take as y equal to eta as interface, so y minus eta will be the equation of basically our interface in the perturbed state, and then we should know that df by dt is 0. In that case, del f by del t plus that uh, uh, q dot grad f will be 0, and we'll get the same equation. From there we can get minus del eta by del t, because y is not depending on this one, and then this grad phi dot del, and then this fy minus eta we can easily calculate. Okay, and then this interfacial condition that we have derived for the incompressible fluid, the condition will be the concept will be same in the, because we are using the same basically our theory, VPF theory. So the concept will be same, that the pressure and these are the normal rotational stresses will be neutralized by the surface tension force, and so we will calculate the effect of tangent that normal stresses, and then we will calculate this condition exactly, but the concept will be same, that the normal stresses at the interface will be covered by the will be neutralized by the surface tension at the interface. So in that case, what we'll do when we need to study the different that the stability, we perturb the interface and then we linearize the interface and got these equations. Remember this equation, when we'll take this equation as basically our uh, mm, we'll take the concern for this equation, del rho by del t plus rho del square phi plus divergence rho gradient of phi is equal to 0. So in the perturbed state this term will be a non-linear term, so we need to neglect this term. Similarly, this is the Bernoulli equation, we need to neglect the non-linear term, and then we'll get the value of del square phi by del t square from the third term, the last term, where we have p is equal to a rho to power gamma. Now we'll use the normal mode technique, and we in that case when we study the two-dimensional flow, we will take phi edge hy exponential I kx minus I omega t, and so in that case we can calculate this del square phi, but in that case this del will be different from the other values, that the del is not exactly del square x by del square pi by, that del is not exactly basically your del 2 by del x square, del 2 by del x square plus del 2 by del y square. So we'll take the appropriate transformation and we'll solve this phi for the case of compressible fluids. And then for the compressible fluids, when we calculate the value of phi, we will have this equation. We can derive this equation from the Navier-Stokes equation for compressible fluids. Navier-Stokes equation for compressible fluids and we know that in case of compressible fluids we have two terms of the normal stresses, that you know that Tij previously we did. So in that case we will get this equation, and here again we can understand this is the pressure E2, these are the normal stresses, and that the normal stresses at the interface will be neutralized by the surface tension. So these are two cases when we have studied the VPF theory for the incompressible fluids as well as the compressible fluids, but in both the cases we found that we are found that we can take only the irrotational normal stresses at the interface, and these stresses neutralized by the surface tension. Now one question arises whether we can use the effect of, or we can include the effect of tangential stresses or not. This is a big question, because when we are studying the interfacial instability, and then cannot neglect the tangential stresses. So one idea that basically modifies this VPF theory and into another theory known as viscous corrections for VPF theory. It is called VCVPF theory. Joseph in 1994 did some work on it. He has suggested that we'll take one extra pressure term into the that normal stress balance, that the P2 minus normal stress is equal to surface tension. So we'll take that P we are taking as P rotational plus P viscous pressure, and this PV is, this term is coined by them as viscous pressure, and they said that at the interface will take an extra pressure. That PV will be the extra pressure, and that PV we will calculate using the mechanical energy balance equation. They have shown that this PV is basically added the effect of tangential stresses at the interface. This Pi is then irrotational pressure and can be obtained by using the well-known Bernoulli equation. So this Pi can be obtained by well-known Bernoulli equation. For incompressible fluid, these are the normal stresses that can be written like this: 2 mu del 2 pi by del n square, that we have already calculated. Now we have to calculate this PV, this extra pressure term, and they have showed that they have that this extra pressure will definitely include the effect of rotational tangential stresses. So in that case, what they did, they have taken a mechanical energy balance equation that previously we have studied, that the rate of change of kinetic energy is basically the velocity do work at the interface, the stresses do work on the surface area of the uh, surface area that bounds the volume V, and the rate of viscous dissipation. Now, this term, this T stresses basically can be written as pressure, normal stresses, and tangential stresses. And then they have they did basically, if P is Pi, that P is only Pi, then definitely these stresses are not zero. And if we can take P as Pi plus PV, if we'll take this one as Pi and PV, then definitely these stresses will be zero, because we are taking that this PV is basically including the effect of rotational tangential stresses. So this term will be included as PV, and then we have compared these two equations as like this, and we will get these two equations. If we compare, the left hand side will be same, right hand side first term same. In the second term, this term is basically governed by this, basically equals to this one, and these are the viscous dissipation terms, so they will not be zero, sorry, they will be equal. So if we compare these two equations, this 1 and 2, so we will get this condition, like integral over the surface A is the surface area that bounds volume V, and this is the normal velocity Un, normal component of velocity Un, and this is the pressure term that is governed by the this tangential velocity Us and tau s. Means with the help of this extra pressure term, we can include the effect of tangential stresses and tangential velocity. So by including the effect of rotational tangential stresses and tangential velocity, we basically can include the total effect of viscosity, and then the VC-VPF theory is gives more accurate result than than the VPF theory, because VC-VPF theory includes the effect of both normal as well as tangential stresses, while VPF theory includes only the effect of normal stresses. But it is not easy to include the pressure term and calculate this value. So generally people are using the viscous potential flow theory. Now, then the one question, how we can calculate this PV, because here we know the uh, as we know the velocity potential, so we know the tangential velocity, we know the tangential stresses, we know the normal velocity. How we can calculate this viscous pressure term, that extra pressure? So it is shown by the that Joseph, as we are taking the flow as irrotational, so the pressure will also be irrotational. Pressure will also satisfy the Laplace equation, because the flow is irrotational, and the velocity basically satisfies the Laplace equation as we did earlier. So with the help of this one we can just write that del square PV is 0, and if it is 0 then definitely we will use the normal mode technique at PV as some Py and this exponential ikx minus I omega t, and then we can just calculate this one, and by putting in this equation, in the particular equation, we can calculate the value of PV, and we will use this value of PV in the dynamical equation and will get the dispersion relation. Thank you. Thank you very much. In the next lecture, in the last lecture, we will apply this theory to the basically our problems in the planar geometry case. I'll study how we can basically how we can use this concept to the problems. Thank you.